line regulation. So, line regulation is usually measured in millivolt, sometimes millivolt, people sometimes also quote it in millivolt per volt, but it is defined as the change in the output voltage when the input voltage is increased by 1 volt. This tells you why some people measure it in millivolt per volt, right, because you are changing the input supply by 1 volt. So, it is the amount of millivolt change when you change input supply by 1 volt. So, some people refer to it in millivolt, some people in millivolt per volt, they are the same thing. So, let us go back to our circuit now. We have 5 ohms, and now we will measure these things at the typical condition. So, we will measure this with no load. Line regulation is usually measured with no load. So, with I load equal to 0 milliamp, right. So, now we said V out when V in goes to V in plus 1 volt. So, we will go from V in equal to 3.2 volt to V in equal to 4.2 volt. So, when V in is equal to 3.2 volt, this is typical. V out is equal to 1.6 volt. When V in is 4.2 volt, V out is equal to 2.1 volt, right. So, delta V out is 2.1 volt minus 1.6 volt, which is 0.5 volt, or if we want to quote it in millivolts, is 500 millivolt. So, in this case, for a simple resistive divider, the line regulation is 500 millivolt, right. Now, you think about it, right, you have a parameter that is specified in millivolts. So, it is already signifying what the expectation is, that it will be single digit millivolt, maybe worst case low double digit millivolt. What we have is a triple digit large millivolt number, and that is one of the weaknesses of the resistive divider. We will get to that in a bit, but this is the calculation for the line regulation. So, it is defined as the change in output voltage when the input voltage changes by 1 volt. So, we went from V in of 3.2 to V in of 4.2, and in this case the output voltage changed by 500 millivolt. That was line regulation. Now, let us calculate load regulation. So, load regulation is defined as the change in output voltage when the load current goes from 0 to the maximum load current, right. In our case, the maximum load current is 100 milliamp. So, when and this again is measured with V in equal to V in typical. So, in our case this is 3.6 volt. So, let us say we have 3.6 volt, you have 5 ohms, and now we are loading it with the load current, this is V out, right. I load equal to 0 is very simple to calculate. When I load equal to 0, V out is just V in by 2, which is 1.8 volt. This is what you get when there is no load current. What happens when there is a load current? In our case, the load current is 100 milliamp, which is 0.1 amp. What happens when there is a load current of 100 milliamps? What you have to do is convert this Norton equivalent to a Thevenin equivalent. Load regulation is defined as the change in the output voltage when the load current goes from 0 to I load max, and the load regulation is usually measured at the nominal voltage. So, in our case the nominal voltage is V in equal to 3.6 volt. So, load regulation will be measured at 3.6 volt. So, we will first calculate what happens at I load equal to 0, then what happens at I load equal to I load max, and in our case we have defined I load max to be 100 milliampere. Once we calculate the output voltage at these two different load currents, the difference between the output voltages is the load regulation. The first case is very simple. We have 3.6 volt, then we have two 5 ohm resistors. There is no load current, which means that V out will be 3.6 by 2, which is 1.8 volt. So, V out when I load equal to 0 is 1.8 volt. So, that takes care of the first data point. The next thing we need to do is calculate V out when I load equal to I load max. So, we have again the same two 5 ohm resistors, and then we have a load current which is 100 milliamp. The simplest way to reduce this equation or reduce this circuit is to convert the current source and the resistor from its Norton equivalent to its Thevenin equivalent. So, the way you would do that is to say that this circuit is the same as V in equal to 3.6 volt, and then we have the 5 ohm resistor, we have another 5 ohm resistor, and the current 100 milliamp multiplied by 5 ohm resistor will be the Thevenin equivalent voltage, which is 100 milliamp into 5 ohm or 0.5 volt. This is V out, right. So, now the voltage between the two resistors, so between this point on the top and this point is now 3.6 plus 0.5. So, we have the current flowing through these 5 ohm resistors I is 4.1 volt divided by 10 ohm, which is 410 millivolt. So, the drop across the top 5 ohm resistor, so this drop, let us say we call it just delta V R1. Delta V R1 is 410 milliamp into 5 ohms, milliamps into 5 ohms, right. So, I will get millivolt when I multiply, no? So far so good, right? So, delta V R1 is 410 milliamp into 5 ohms, which is 2050 millivolt or 2.05 volt, which means V out will be 3.6 volt minus delta V R1, which is 3.6 volt minus 2.05 volt, which is equal to 1.55 volt, right. So, when we had no load current, the output voltage was 1.8 volt. When we have 100 milliamp load current, the output voltage is 1.55 volt. So, I should like I said, this is I load equal to 0, this is I load equal to 100 milliamp, right. Let us just free up some space here. So, I am just going to move this here. So, load regulation delta V out equal to V out at IL equal to 0 minus V out at IL equal to 0.1 ampere. 0.1 ampere is 100 milliamp. This is 1.8 volt minus 1.55 volt, which is 0.25 volt or 250 millivolt. So, it is worth noting that, and 250 millivolt is a very high load regulation, right, and it is worth noting that even though we have chosen very small resistors, our resistors are only 5 ohms each, even though we have chosen such small resistors, the regulator we have built is still performing very poorly with respect to output current. As you keep reducing the resistance, you would think that it will remain invariant with respect to load current, but even at 5 ohms of resistance, the invariance to load current is not very good. So, when the load current changes from 0 to 100 milliamp, the output voltage is changing by almost 250 millivolt, right. So, this is something for us to keep in mind. What we will do next is, okay, we got 250 millivolt load regulation. What sort of standby current do we get? What sort of current limit do we get is something we will look at. I hope you understood the load regulation calculation. The next thing we are going to calculate is the standby current. So, we calculated load regulation which is delta V out when load goes from 0 to I load max. Let us now calculate the standby current. So, again we have so this we will calculate at 3.6 volt. Standby current is I standby current from V in when I load is 0. So, in this case, if I load equal to 0 implies I standby is just 3.6 volts by 10 ohms, which is 360 milliamp or 0.36 amperes. So, this is 360 milliamperes, right. You know, I remember, I hope you remember me telling you that standby current is typically quoted in microamperes. So, if we have a circuit like this, then the standby current is going to be several orders of magnitude higher than what we can tolerate. Now, you can argue that, oh, it is because the standby current is so high because my 5 ohm resistance is there, because I have put in such a small resistance of 5 ohms. What you would realize by now is, suppose I were to make that 5 ohms into 50 ohms, then my load regulation will immediately go from 25 millivolt to 250 millivolt. So, even if I want to reduce the standby current to 36 milliamp by increasing the resistors by 10, that will come at the cost of load regulation, right. So, there is a trade off in a circuit like this between the amount of standby current I can tolerate and the amount of load regulation I can get, at least for an implementation like the one we have, right. So, you know, why is standby current quoted in microampere? Why is standby current such a big deal, right? Sometimes I worry it does not get the importance it deserves. Now, let us say, let us try to do a, go to a new page and let us try to get a sense of how low should right. Now, in general, you know, every question is followed by more questions, right, and it is important to start from here and keep asking the right questions. So, to know how low should the standby current should be, we should ask ourselves how much shelf life do we want? Right? I mean, you imagine this, no? You as a user you can say, okay, my customer used the product in March, and then let us say 1 quarter passes, he uses it again in June, he shouldn't have to put it for charge. If he turns it on, it should turn on. That is my expectation, which means that the shelf life you are expecting is 90 days. Or you picture this, you say that, you know, I boxed the product, I made the product, I boxed it, I sent it to my warehouse, from the warehouse it went to the distributor, from the distributor it went to the retailer, and then it was on the retailer. The retailer is a store, let us say is a Chroma store, and on the shelf of the Chroma store it sat for some time before a customer actually bought it. So, if it has to go through all of this, and at that point you do not expect when the customer is buying it that the first action will be a charging action. You expect that when the customer turns it on, in that situation the device will turn on. So, that now let us say I think, okay, you know, I am, or maybe I am boxing it here, I am shipping it through sea to the US, where it will go through the distributor to retailer chain. So, I want maybe 6 months shelf life. So, the number of days of shelf life you want dictates what the standby current needs to be, right. So, let us say I have a, for simplicity's sake, I have a 1000 mAh battery and I want 6 months or 180 days of shelf life with 50%, I am willing to accept 50% discharge in 180 days, right. So, let us say I started with 75% charge, okay, after 180 days it goes to 25%, I will live with that. So, the calculation you would do is you say, okay, I can tolerate 50% discharge. So, 500 milliamp hour is the amount of discharge I have. This must be equal to my standby current multiplied by the number of hours in 180 days, right. So, into 180 into 24, right. That is the amount of standby current. We will try to calculate it in microamps. So, I standby is 500,000 microamp hour divided by 180 into 24 hours. So, 50,000 by what is 24 into 18, we will sort of make the numbers friendly, we will say this is about 500, right. 25 into 20 is 500. So, between friends we will say this number is 500. So, you have 50,000 divided by roughly 500, which is 100 microamp. So, if you want, if you have a 1000 mAh battery and you want 6 months of shelf life, then your standby current should be less than 100 microamp, right. We are currently at a standby current of 360 milliamp. So, what 360 milliamp standby current essentially says is that, you know, you turn your device off, 2 hours later, 3 hours later, maybe the battery will be fully discharged. So, obviously, we are playing around here with a very simple voltage regulator. So, it is to be expected that we will see numbers that make that are practically useless, but it is good to understand, oh, okay, this is the limitation of what I am trying to of the proposal I have, right. So, keep in mind that standby current is directly correlated to shelf life, and depending on the amount of battery size you have, you are looking at standby current in the tens to hundreds microamp or 10 to 100 microamp to be able to support a 6-month shelf life. For just going back to our example, in the example we had standby current is 360 milliamp, right. Then there is load current, which in our case we have already defined it. So, we do not need to calculate it again, it is 100 milliamp. The last thing we have to calculate is the short circuit current. So, again we will calculate this at 3.6 volt. Actually, there is one thing that we have to calculate with respect to load current. So, we have to be sure that can the regulator provide I load at its minimum value, right. So, what is the minimum value? Let us say that my battery is 3 volt, because 3 is the minimum value. I have 5 ohm, 5 ohm. Now, I am going to draw 0.1 ampere. Will this voltage be above, will this voltage be above the rated minimum for the active circuit? So, you might recall that when we started off, we said that our active subsystem requires a nominal voltage of 1.8 volt, can tolerate a max of 2.1 volt and a minimum of 1.2 volt. That is what we started off with. So, we can say, okay, now we need to make sure that this voltage should be greater than 1.2 volt in the presence of load. So, the calculation that we had done with respect to load regulation can come in handy now. We know that the load regulation is 250 millivolt. When the input voltage is at its minimum and there is load current, so V out when V in equal to 3 volt, I load equal to 0 is 1.5 volt, which means that V out when V in equal to 3 volt and I load equal to 100 milliamp will be 1.5 volt minus 250 millivolt. 250 millivolt I can write as 0.25 volt. This will be equal to 1.25 volt. You might recall that we had said the minimum acceptable voltage for the active circuits is 1.2 volt, right. So, we have margin, but barely. So, when the input voltage is at its minimum level, we have 50 millivolt of margin. We need to be above 1.2 volt to make sure that the active circuit can work. We will be at an output voltage of 1.25 volt. So, this is a good calculation to do to make sure that across the entire range of input voltage conditions, the regulator still presents the correct voltage to the active circuits that it is powering. So, now let us calculate the short circuit current. Now, the definition is straightforward, right. It is the amount of current when V out is 0. So, this again we will measure at 3.6 volt. Now, I am shorting this, right. This is V out. So, V out goes to 0. So, the current here will just be I is equal to I short circuit is just 3.6 volt by 5 ohms, which is 720 milliamperes, right. So, that is the correlation between the short circuit or that is the way to calculate the short circuit current, right.